Hello guys, welcome back to Brithany and Joss. My name is Joss and today I'm going to be explaining equilibrium of a particle and free body diagrams, specifically in statics. So what exactly is equilibrium of a particle? So equilibrium, as we talk about it in physics, means that a system is going through absolutely zero acceleration. So this means that either we can have a system that is staying completely still or has a constant velocity, so aka zero acceleration. When we talk about equilibrium specifically in statics, so static equilibrium, we're talking about a system that is staying still. So what is a free body diagram and how do we use it in statics to help us solve problems? So a free body diagram is basically a representation of our system, and it's breaking down into simple elements so that we can see all of the different forces acting on the system. We can see the weight, we can see the tension, we can see different forces, friction in some cases when you take physics. More specifically, in statics, we don't have to draw out all of the friction and all that because we don't have any movement. So I'm just going to give an example of how I would draw the free body diagram for this lamp fixture that I've drawn right here. We need an object to represent the weighted object. So that in this case it's going to be this. So this is the object that's being hanging. I don't have to add that many details because it's just supposed to be a simple graphical representation of what I'm doing. And this is going to be the string that is hanging from here. So whenever we have an object like this, obviously it has a mass, and the mass is always going to pull downwards because of gravity. So this is my mass times gravity, and that's always going to be going downwards because gravity goes downwards. And whenever I have a string, I also have tension in the string, because whenever I have this weight that's pulling down, it's going to also pull down in the string and cause tension. So we can write T for tension here. So that's how you would draw the free body diagram for this hanging lamp here. So now that we found the free body diagram for that previous lamp, how would we do a free body diagram for something like this, where it has elements in not just the y direction, but also the x direction? So let's say we were given this. So I've defined the positive x and y axis, and I have the angles that are in between here. So I want to start off by drawing the weight that we have. So this is going to represent this lamp fixture right here. This is the part that holds the weight. And we have two cables. We have cable AC and cable BC. And whenever we have strings, we have tension in those strings. And whenever we have this object, we have a mass. So this mass is always going to go down, mg. And we have tension in the x direction for this line. So this is tension AC in the x direction. And then we also have the tension AC in the y direction. And then I'll do this in a different color to differentiate. We have the tension in BC in the x direction, and the tension BC in the y direction. So this one is actually since I've defined my x and y axis like this means that this is going to be in the negative x direction. This one is the positive x, this one is the positive y, and then this is going to be negative because it's in the negative y. So now that I have that all in my diagram, we can use our diagram, now that we've drawn everything out, to make our equation. So the sum of all of the forces in the x direction, let's see, all of our x, this one is an x, this is an x, and then all of the rest are y directions. Negative t ACX plus TBCX. And T just stands for tension. And then all of these are always going to be equal to 0 because the sum of the forces in all directions are equal to 0 in statics. So now that we have that, let's do in the y direction. So the sum of the forces in the y, this one is a y, this one is a y, and so is this one. So let's write that down. We have TACY plus TBCY minus MG. And then that is always going to be equal to 0. So our free body diagrams can help us find our equations and help us solve for unknowns. So let's see how drawing a free body diagram can help us find our unknowns. So here I have this problem that tells us to find the tensions in all of the cables, and the only bit of information that we're given is that this weight here, that this weighs 60 kilograms. So with that, how would we find the tensions? So first of all, we have to break this down into free body diagrams. We need to make a free body diagram for each of the essential points that we have. So we have one here where we have a bunch of forces acting on this point and here on this point. So the first thing that we need to do is define our x and y axes. So this part people can do differently. I like to define mine where we have the most going on, so like right here in the middle where we have like all these forces. So B would be my 0, 0, and I would define it like this. You can do it based on anywhere you want pretty much, but just make sure that you remain consistent throughout your problem solving, that you're making sure that the negative x and negative y components stay negative or positive. So what we're going to start off with is our free body diagram for point B. So I have my cable AB right here, BC, and BD. And this is point B right here. So I have tension in all of my cables, so I want to draw out my tension. So this one goes in both x and y directions. It goes in the negative x direction, so the tension of A in the x direction, this is negative because it's on this side. And then I have the tension in the y direction, which is positive because it's in the positive y. So if it was down here, it would be negative, but since it's not, it's up here, it's going to be positive. So tension in the y direction. And then we also have for CB, tension in the CX and tension in CY. And then we have this tension down here that only goes in the y direction, and that is the tension of BD in the y direction. And then the only other free body diagram that we're going to have to make is of our object. So we have our object, our weight here. We have the weight that's dragging it down, which is mg. And we have the tension. This is the same tension, but it's represented differently on our different diagrams. This is T BDY. So this and this are the same. So now that we have that, let's make all of our equations. So let's make the equations for this one first. We have the sum of the forces in the x direction. So our x direction, this one is in x direction, this one is in the x direction. So it's going to be negative T A in the x direction plus TCX in the x direction. And all of these equations are always equal to 0. Now let's do in the y direction. So the sum of the forces in the y for this one, we have, these are all in the y. So we have TA in the y direction plus TCY and minus, because this is pulling down, minus TBDY. And as always, this is equal to 0. Now we also have from our second free body diagram this over here. So this is the sum of the forces in the y direction. And it states that TBDY minus mg is equal to 0. So now we can start adding values to our equation. So as you can see, let's start with this equation right here, our fx. So f of x equals negative t. So TA, so this force right here, in the x direction, we can see that we're given this little triangle. In the x direction, it is 4 right here. So we're going to write TA in the x direction 4/5, because that is the ratio of the tension that is in the x direction. For TCB, this one, we can see that we're given that this is a 45-degree angle. So using our basic knowledge of triangles, the x, aka this side of the triangle, is the adjacent angle to the 45. So the tension in the C, we're going to do cosine 45. And then as always, equals 0. So now we can do in the y direction. In the y direction for this one, we have 3. So TA, 3/5, because that is the ratio in the y direction. And then in our TC, the opposite angle will give us, or the opposite side will give us our y. So sine 45. And then this one, negative TB dy, and then equals 0. So these equations are going to be what helps us find our tensions. So we have, as of right now, we have 1, 2, 3 unknowns. So let's see if we can solve for any unknowns. So we have this negative TB dy, and we have this second equation from our other one, which can give us the value for that. So let's try and see if we can find the value of TB dy. So TB dy, and again, that's this tension right here, minus mg is equal to 0. So let's bring this mg to the other side. And we know that the mass in this case, or the weight of it, is 60 kilograms. And gravity is 9.81. So So that gives us that TB/dy is equal to 588.6 newtons. Now that we have this, let's do some algebra and let's solve for our forces. So now that I have the value for this one, we have two equations and two unknowns, which means that we can use one of our equations to solve for the other one. So I'm just going to use this first equation to solve for, let's do TC. So I have here negative TA 4/5 plus TC cosine 45 equals 0. So let's solve for this. So first we're going to add this C side. And then to get rid of the cosine and get this TC by itself, we're going to divide by cosine 45. So that leaves us with TC equals 1.13 TA. 4/5 divided by cosine 45 is 1.13, so that's how we get this. So now that we have this, let's plug this in to this equation and let's solve for all of our forces. So I have here in my FOI equation, I'm just going to plug in this new value for TC, so we only have to use one variable and we can solve for TA. So TA 3/5 plus, and we're not going to use TC here, we're going to use this value for TC. So it's going to be 1.13 TA sine 45 minus, and TB/dy, we know from right here that it's 588.6, and that equals 0. So with some simplification, since these are both now the same variable, I can just combine them. So 1.13 times sine 45 is just going to be 0.8. So 3/5 plus 0.8 is going to give us TA 1.14. And all we're doing is just combining these, because we can do that because it's the same variable. And I'm going to move this to the other side of the equation. $588.6, and then pretty simple solve from here. Divide 1.14, and that's going to give us that TA is equal to 420 newtons. So now we can plug in this known TA value right here, so we can leave TC as the only unknown in this equation and solve. So we're going to sub this in, so negative 420 times 4/5 plus TC cosine 45 is equal to 0. And when we set it up to solve for TC, we're going to get and we're going to end up with TC is equal to 475 newtons. So in conclusion, free body diagrams are a way for us to visualize our systems and help us derive equations from them. I hope that you guys learned a lot. Let me know if you have any questions, and thank you so much. Bye.